How many games of Yahtzee are there? There has been extensive work done to calculate single-player Yahtzee strategy. With perfect strategy, you will score an average of 254.6 points per game. However, I could find little work on the topic of multiplayer Yahtzee. In Olaf Vancouver's Advantage Yahtzee, the gold standard for Yahtzee strategy, he briefly touches on multiplayer strategy in a short 5-page chapter. However, the bulk of the book focuses on single-player strategy. But Yahtzee is a finite game. There are a finite number of outcomes for the dice and a finite number of decisions you can make. So there must be a precise optimal strategy for every single multiplayer Yahtzee scenario. What is one way to solve a finite turn-based game? This type of game can be solved with a decision tree. To make the most comprehensive decision tree, you must account for every single possible outcome that can occur. Each branch can represent either a possible player decision or a random probabilistic outcome like a dice roll. The construction of such a decision tree leads to the question: how many unique possible games of Yahtzee are there? Vancouver's chapter surrounding multiplayer strategy can be summarized in 2 sentences. If you're far behind, play more aggressively. If you're leading or within striking distance, stick to the optimal single-player strategy. This intuitively makes sense. It's similar to the reason why a hockey team might pull their goalie if they're down by 2 points with only 3 minutes left in the game. The team needs at least 2 goals to send the game into overtime, and anything less than 2 goals will result in a loss. Yes, by pulling their goalie, they're making it much more likely that their opponent scores on them. But they are also increasing the likelihood that they themselves score on their opponent and make a comeback. Pulling the goalie decreases the expected value of their spread. Notice how the red dashed line is to the left of the blue dashed line. But it increases the variance, which is a necessary trade-off in a comeback situation. In Yahtzee, the same principle holds true. Consider a scenario where you are 45 points behind your opponent on the second-to-last turn. Your open categories are large straight and Yahtzee. Your opponent has one open category, which is full house. On your first roll, you roll 2, 3, 4, 4, 5. The optimal single-player strategy says to hold the 2, 3, 4, 5 and re-roll the last die. You'll roll a large straight 5 out of 9 times in your last 2 rolls. In single-player, the 4 out of 9 times you miss the large straight, you should score 0 in Yahtzee and go for a large straight again on your last turn. However, our multiplayer scenario is different. In our multiplayer scenario, a large straight will still put you 5 points behind your opponent, and you'll still need a Yahtzee on your last turn. In our multiplayer scenario, it's much better to hold both 4s and re-roll 3 dice to try to get a Yahtzee. If you miss your Yahtzee, you should score 0 in large straight and try to get a Yahtzee again on your last turn. You'll still lose almost all of the time, and your expected score is much lower than either of the other 2 strategies. But if you hold 2 4s and go for a Yahtzee, you'll win about 4.94%, and you'll only win 3.86% or 2.56% of the time if you use one of the other strategies. This is a fairly basic example, but the same principle holds true for more complex Yahtzee positions. Because Yahtzee is finite, it is possible to quantify these deviations in the single-player strategy and calculate exact win likelihoods. And if we know the exact likelihoods, then we can make the optimal decision in any multiplayer scenario. If a computer can solve for a complete multiplayer decision tree, they would be able to output the most optimal decision in any given multiplayer scenario. But is a decision tree for Yahtzee a realistic solution? Let's look at the math. There are 13 categories in Yahtzee. Every turn you roll 5 dice up to 3 times. After every roll, you can either choose to re-roll any number of your dice or score immediately and end your turn. At the end of a turn, you must score a category. That means the game will be over in 13 turns no matter what. Let's break our question down into a smaller problem. Each of the 13 turns is independent from each other. So now we have a slightly simpler problem. If we can find out how many possible unique turns there are, we can easily calculate how many possible unique games there are. Let's take a look at just the very first roll. Nothing is scored and you must roll all 5 dice. How many possible first rolls are there? The first die has 6 possibilities, so does the second die, and the third and fourth and fifth. That's 6 times 6 times 6 times 6 times 6 equals 7,776 unique possible first rolls. You may notice that some of these combinations are repeated. For example, there is only one permutation of rolling all sixes, but there are 5 permutations of rolling 4 sixes and 1 5. And there are 120 permutations of rolling 1 2 3 4 5. For the purposes of our decision tree, we will consider these repeated combinations as separate. While this may not be the most intuitive examination, it is the best place to start from a game theory perspective. Why is that? This makes every branch of our decision tree an equal probability. If we were constructing our decision tree from our 252 combinations, we would also need to calculate and consider the simplification for each of those 252 combinations. A computer can make this, but it's not realistic to create this tree by hand with pencil and paper math. So to keep things simple for this video, we will consider all 7,776 permutations as unique, knowing that each of them has exactly a 1 in 7,776 chance of occurring. You can imagine we're playing Yahtzee with colored dice, and rolling 4 sixes and a 5 on the yellow die is considered a different game from rolling 4 sixes and a 5 on the blue die. So there are 7,776 possible outcomes after our first roll. After the first roll, we will reach our first player decision. The player must decide which dice to hold. He can hold no dice, only the first dice, the first and second dice, the first and third dice, etc. This can be represented by the sum from k equals 1 to 5 of 5 choose k, where k is the number of dice being re-rolled. This sum is equal to 31. The player can also choose to score immediately and end his turn, which is another possible outcome. So there are 32 possible ways to continue our turn. However, not each of these 32 continuations will have the same number of unique branches in the very next step. For example, if you are only re-rolling 1 dice, then there are only 6 unique outcomes your dice can be after your roll. However, if you are re-rolling all 5 dice, then there are once again 7,776 unique possible outcomes for your dice after your roll. So to represent our second and third rolls, we must not multiply by 6 to the 5, but instead multiply by 6 to the k. Putting all this together, we can write a recursive function to determine the number of unique paths based on n rolls of 5 dice, where you can choose to hold any number of dice or score immediately after each roll. Our summation simplifies to 16,806. In Yahtzee, there are 3 rolls per turn, so solving for f of 3 will tell us how many total unique possible ways one Yahtzee turn can unfold. That number is 132, 799, 817, 413, 158, 223, 968, or 1.33 times 10 to the 20th. And this is only the number of possibilities for a single turn of Yahtzee. A full Yahtzee game has 13 turns, which means we aren't done yet. If someone scores a large straight on their first turn and a small straight on their second turn, that game is different than someone who scored a small straight on their first turn and then a large straight on their second turn. Even though the final result after 2 turns may be the same, the strategies, probabilities, and expected values to arrive at each of these 2 outcomes will be different. So it's safe to say that these are 2 unique games. We must then determine how many possible ways there are to order 13 different categories. Luckily, this is a very easy calculation. If you have 13 items and you want to know the number of unique ways to order all 13 of them, the calculation is simply 13 factorial, or 13 times 12 times 11, all the way down to 1, which is equal to 6.23 times 10 to the 9th. So we have determined that there are 1.33 times 10 to the 20th unique ways to play an individual turn, and 6.23 times 10 to the 9 ways to order scoring 13 categories. Therefore, the number of unique ways a Yahtzee game can occur is this huge number, which I'm not even going to try to read. But what if I told you that this was only half of the digits? Well, I'd be lying again, because this is the real number, which has so many digits that it doesn't even fit on a single slide. This number is so astronomically large that there is no good way to grasp its enormity. If you had a supercomputer that could perform 1 trillion calculations per second and started running it at the beginning of the universe, it would only have completed about 10 to the 29 calculations. There are 10 to the 80 atoms in the entire universe. Consider every single atom in the entire universe. Now imagine that every single atom represents a copy of our entire universe. And consider every single atom within those nested universes. You could assign a unique Yahtzee game to every single atom within every single nested universe, and you would still have over 10 to the 111 unique Yahtzee games left to assign. What does a 1 in 2.49 times 10 to the 271st chance look like? It's equivalent to all these incredibly unlikely things. And this is just for the number of unique possible single-player Yahtzee games. For the number of unique possible two-player Yahtzee games, we square this number, resulting in 6.19006 times 10 to the 542 possible unique two-player Yahtzee games for our decision tree. So, is a decision tree a realistic solution for determining the optimal two-player strategy? No. The number of unique possibilities is so large that no computer would ever be able to hold all of the unique possibilities in its memory, let alone retrieve or analyze them. A perfect multiplayer Yahtzee player is much more likely to arise from advanced computer algorithms that can analyze a given position in real time, similar to modern chess engines like Stockfish. Be sure to like this video if you enjoyed. If this video does well, I may release more of these types of videos in the future or make a follow-up to this video. Thank you for watching and have an excellent day.